All right, so this is the second of my How to Draw Free Body Diagrams series. In the first one, we looked at things that were like on a flat surface or falling through the air where you didn't have anything at an angle. When we're doing things at an angle, sometimes you want to rotate the frame of reference. So I'm going to show you what that looks like on here. So imagine that our situation is that we have a box that's sitting unmoving on an incline. So I already drew the picture. That looks something like this. And when we have a situation like this, we have two options. So our first option is that we could have our X and Y axis with the, like, Y is parallel to, like, pointing directly down, and X is pointing directly to the side. Alternatively, we can turn it so that our X axis is parallel to the surface and our Y axis is perpendicular to the surface. So I'm going to show you what that looks like. We're going to draw a rotated frame of reference like this. So our x-axis is going to be parallel to our surface. Y-axis is perpendicular to our surface. So for our forces, so we have this, we want, again, always look for clues in the problem or clues in the situation that will tell you if you have balanced or unbalanced forces. In this case, it's unmoving. So what does that tell me? Is that I have to have balanced forces. And they're going to be balanced in my x direction, and they're going to be balanced in the y direction, even though the x and y don't align with like our sort of our regular upright frame of reference. All right, forces. So let's draw a dotted line around this, just so we can tell contact forces and non-contact forces. So it looks like I have on here, I have the ramp. Generally, since this is the one that's preventing it from falling into the ramp, we're going to call that the normal force. We have the earth. Now, the earth is going to be not on the x or y axis because we tilted our x and y axis. It's going to be more like this. And, all right, so I'm going to stop there. Reason being is that a lot of people will look at this and they'll be like, I don't know if there's friction or not. So one of the things that I want to show you is how to recognize if there's going to be friction. So let's draw our free body diagram, and then we can come back to that question of, is there static friction? Static friction being the frictional force that holds things in place and prevents them from moving. All right, free body diagram. So I'm going to draw the x and y axis, but again, they're going to be rotated to the side. So I'll draw those in red just so we can see what's going on here. So here's our x-axis. This should be at the same angle as this one. It's not perfect, but you should try to have it. So x is going to be on the side. Y is going to be like that. I'm going to exclude the ramp because the only thing I'm trying to draw here is my box. So I'll represent my box with a, well, let's represent it with an actual box. All right, here we go. Box is at the center of my diagram. Looking at my forces, so I need the force of the earth, aka gravity, to be going straight down. And you might be saying, why is it straight down? I thought this box would, like if I had a really slippery surface, this would slide down the hill. The answer is that gravity, or the force of the earth, is always directly towards the center of the earth. And the center of the earth is not down this ramp. The center of the earth is towards the ground. All right, so I'm going to call this, here's my force of the earth. And then we have our normal force. Normal force, by definition, is always going to be at a right angle to surface. And it's never going to be going into the surface. It's always like a support force. The normal force comes from the atoms in one item not wanting to move through the items in the other atom, or the atoms in the other item. So like these atoms don't want to move through the atoms in this ramp. All right, so I'm going to draw my normal force, and it's going to look kind of like this. And by the way, I need to start labeling these, but this should be force of earth on the box. And this is going to be my normal force, which I'm going to call the force of the ramp on the box. All right, so next thing is, what do I do about, so in class we talked about this thing called vector components. And so I'm going to zoom in on this. And I'm going to show you what I'm talking about when we talk about vector components. All right. So on my free body diagram, we can see that there is an angle that is not 90 degrees between this force vector. A vector is any quantity that has a direction and a magnitude. So this force vector and the y-axis. There's also an angle, a non-zero, non-90 degree angle between this force vector and the x-axis. So what I'm going to do is I'm going to break this into two other vectors, which we call vector components. One of them is going to be pulling, as we can imagine, it's the part of gravity that would make this box slide down the ramp, right? So that's going to be parallel to the surface. And then we're going to break it into another part that's pulling it directly into the ramp, which is going to be looking like this. Now, the reason I'm going to draw it the way I do is that in trigonometry and in geometry, we use, like the way that we do vector addition, one of the ways you can do it is just by adding up arrows. So I want to make sure that they're the right length on here. And all right, I'm going to use green. Do I have another color? Yeah, I'll use green to represent those vector components. All right, so the way that I would do this is you want to think about, I want this to be the hypotenuse of a triangle, a right triangle. And so one of the sides of that right triangle is right here. I'm going to highlight that in green. Right here. And the way that we're going to call this is going to be the force of the Earth on the box in the y direction. So I have like so many subscripts here. Now, the other part of this would be right here, right? So we can see that I have a right triangle between this arrow, this vector component of the force of the Earth in the y direction, the force of the Earth itself, which is the hypotenuse, and then this amount. This represents the amount of this force that's pulling it down the ramp. Now the thing is that in a free body diagram, I always want to have, all arrows coming from the center. All right, and I'm not, like currently I have this one arrow. If I were to draw in this right here, it wouldn't be centered like with all the other arrows. I need to show these all, like all these different forces pulling in different directions. So instead what I can do, and you're allowed to do this with vectors, is you're allowed, as long as you keep the same length and direction, you're allowed to move them from one place to another. So I'm going to pick this up and I'm going to redraw it, same length, same direction, but like I can see that this is parallel to the x-axis, so I'm just going to draw it on the x-axis. And it's going to look like this. And this is going to be my force of the Earth on the box in the x direction. So this thing right here, let's give it a title. We call this the x component. And we call this one the y component. And when we use the x and y axis in this situation, we're using them like a math teacher would use them, but in math you learn that they don't always stand straight up. You can sometimes just tilt them to the side. All the math works out and would work out the same as if we had our x and y axis like directly horizontal and vertical. The math will work out in the end, even you're allowed to do this tilting. All right, so now instead of treating the force of the Earth like it's down, I'm going to say that part of this force of gravity or force of the Earth would make this slide downhill, and part of it would make it go in here, right? I have the normal force is going to oppose that. So remember how we drew our congruency symbols. This and this should be congruent. So the way that I would get the force of the ramp is by saying how much of the force of the Earth is directed along our tilted y-axis or perpendicular to the ramp itself. And my normal force, or the force of the ramp, has to be enough to oppose that. Now, in our situation, if we go back, it says this box is sitting unmoved on an incline. So what that means is that I can't just have balanced forces in the y direction. I also have to have balanced forces in the x direction. So I'm going to come in with another force. And this one, I'm like, it's a real force. I don't have to break it into vector components. What's preventing it from sliding down the ramp is that there's like little bumps in the box itself and on the surface. And we call that friction. So the force of friction, in this case, it has to be the same amount as my force of the earth in the box in the down the ramp direction. And so that's going to go like this. And I can show some tick marks over there. This is my force of friction on the box. All right, and so then in the end, we can see that our force of friction is the same as the force of the earth, the box in the x direction or down the ramp. The force of the ramp on the box is the same as the force of the earth in the box. Those two are identical, but in opposite directions. And this is what our free body diagram would look like. If I was drawing it, I would want to show that these are vector components in some way, either by using dotted lines or by using another color, but something to show that I don't actually have 1, 2, 3, 4, 5 forces on it. Really, in this case, I would have 3 real forces: the force of friction, the force of the ramp, and the force of the earth, and the other 2 are vector components. All right, that's it. Enjoy drawing your free body diagrams.